Okay. Hi, everyone. Um, so I hope you all had a good weekend, and I hope the first homework assignment wasn't too bad. I know it was a little bit on the long side. I'll try to get them down a little bit. I just posted the uh, the second one earlier today. I don't know if you saw that, uh, but that one. So like at the very end, it's the last collection of problems is a little bit longer, so I extended the deadline for that one to Sunday instead. So hopefully that's like also manageable. Uh, anyway, so before we jump into the exercises that I had planned, uh, if you have any questions, feel free to ask them now. Oops. Oh yeah, I see some people are still coming in. So okay. Well, if there are no questions, then I suppose we can just go ahead and start here. So I think as a warm up, kind of, I would like to do this problem because a part of one of the proofs, which is sort of like one of these proofs where there's like one statement for like increasing sequences and then another statement for decreasing sequences. I'd like for us to go through the proof of the statement for the decreasing sequence. And what I want you to do is try not to refer back to the proof for the increasing sequences. Okay. So this is just a warm up. It should be pretty simple anyway. So this is prove theorem 10.4 part 2, which says that if Sn is an unbounded decreasing sequence, then Sn goes to negative infinity. Okay, so just yeah, I guess I can I'm actually going to hold off on putting you guys into groups for now because I think there might still be a couple people coming in, and it's sort of hard to like reconfigure the groups after I make them the first time. So for now, let's just all, you guys can think about this on your own. And like I said, try, if you can, try not to like refer back to the book or anything when you're doing this. Just try to like come up with the argument yourself, because hopefully by this point, these kinds of proofs are starting to become a little bit more familiar. And so hopefully you guys are starting to get more of the instinct for like how to just formulate this argument, from scratch. Okay. So yeah, let's just take like, I don't know, 6 or 7 minutes or something. So we can resume at 5, like 17 or something. All right. Okay, so hopefully that wasn't too bad. So let's prove this here. Actually, let me like clear this stuff. So, right, we want to show let Sn be an unbounded decreasing sequence. We want to show that Sn goes to negative infinity, right? So the first thing to say here is that, well, the fact that Sn is unbounded and decreasing means it is unbounded below specifically, right? Because remember that unbounded technically just means like unbounded in one of the two directions, but because it's decreasing, in this case, it specifically has to be unbounded below. Oh, sorry, below, right? So, which means, right, that for all m, right, there, at least we can say that there exists some n such that Sn is less than m, right? So let's say, let m be a real number, and we want to find a place where Sn becomes less than m and stays that way forever, right? But then it's sort of like easy because the fact that the sequence is decreasing means as soon as we find a single term in the sequence that's less than m, then it'll stay less than m after that point. So this thing, this fact over here tells us that there exists a capital N, right, such that Sn is less than m, and then for n greater than capital N, Sn is less than or equal to Sn, which is less than m. Okay? So that's it. Any questions about that? Or for the people who got here while we were in the middle of this, if you have any, generic questions, I'm happy to take those now. Okay. So, all right, with that out of the way, then I would actually like to do one of these problems about recursively defined sequences, because I think that those are just a nice illustration of why the monotone convergence theorem is really useful. I think I covered something similar to that in lecture. So I know like none of the homework problems from this section are specifically about that, but I still think that it would be like a healthy exercise for us to do. So let's do one of those. Actually, yeah, let me here, and then all right. So let's try this one. And I'll put you guys into groups for this one. So let S1 equal 1 and Sn plus 1. And then after this, I think what we can do is I have two problems in mind about, one would be like, I'll describe a sequence for you and have you guys basically determine just like what the lim sup and the lim inf are, because I think that's just a really handy thing to do. And then I'll also give you another question, which is about coming up with an example of a sequence that has a certain weird collection of properties. Because, I love those problems. So, all right. So here's the rule for this one. 1/3 Sn plus 1. Okay. Hold on. It's a little bit weird looking. Okay, so this is the so the sequence would be like 1 and then what, 2/3, and then you'd get like 5/3, so 5/9, I believe. Right. So you see how to to get each one, you just apply this rule one more time, basically, right? So it's kind of broken up into, oh yeah, okay. So I'll break it up into a couple parts for you guys. So use induction to show Sn is greater than 1/2 for all n, and then show Sn is decreasing, and then conclude Sn converges, calculate the limit. Although for the limit calculation, you don't have to you don't have to prove that the number you come up with is actually the limit. Okay. So all right, I'll put you guys into groups now. Here we go. There we go. And great. So yeah, let's take like 10 minutes. So we'll resume at 5:33, I'll say. All right, so hold on. Let me. There's this really weird glitch. My Zoom has like this super weird glitch where sometimes if I like mess around with the various windows and stuff, then like the bar at the top of my whiteboard goes away and I can't like move it around on my screen. I think I just have to like restart the share. Hold on. Stop this. And then just do that. Ah, yeah, okay, great. Got it. So anyway, so let's do this. So let's first show that Sn is bigger than 1/2. Okay. So we actually kind of have to do this by induction, which is what was suggested, right? So so show Sn is bigger than 1/2. Clearly S1 is bigger than 1/2, so that's the base case, right? So now suppose Sn is bigger than 1/2 for a particular n, right? Then Sn plus 1 is 1/3 Sn plus 1, which is greater than 1/3 times 1/2 plus 1, right? Since we assumed that Sn was bigger than 1/2, and this is literally just 1/2. Okay, so that's the whole inductive argument. So now let's show that Sn is decreasing. So basically, let's see. So we want to show that 1/3 Sn plus 1 is less than, well, less than or equal to Sn, right? This is the inequality we want to show. And so we can just kind of manipulate this. So this is equivalent to, if we just subtract 1/3 Sn from both sides, right? So then we get 1/3 is less than or equal to 2/3 Sn, right? So that's true if and only if, if you multiply by 3 on both sides and then divide by 2, right? Also, yeah, multiply by 3/2 on both sides, and you get 1/2 is less than or equal to Sn. So basically, you can, if you want to really, sort of reverse this, if you start with 1/2 is less than or equal to Sn, then you can kind of just like do these manipulations backwards, and then you'll end up with this one. So Sn is decreasing, right? Are there any questions so far? I hope I'm not going too fast. Okay. So then what we've shown is that, so and it's bounded below, right? That was the first thing we did, was we showed that it's bounded below by 1/2, right? So Sn converges. And then, as you might be aware, the way to calculate the limit in these cases, the limit L satisfies, or S if you want, I don't know, to be consistent here. The limit S satisfies 1/3 S plus 1 equals S, right? So this is saying that S is a stable point of the iteration here. So there's basically, the way you get Sn plus 1 is you apply a specific function to Sn, and S is a fixed point of that function. So if you solve this equation, I think you just get S equals 1/2. Yeah. Okay. Any questions about that? So we'll actually show, I mean, I intend to prove for you guys later when we talk about functions, when we talk about like continuity of functions and stuff, right? Here it's like, I just want to tell you, sort of explain this to you guys. So f of x, if you define f of x equals 1/3 x plus 1, right? Then Sn is, f of and so on. Oh, of 1, right? Where there are n instances of f, right? So to get the next one, you just apply f again every time, right? And so, well, one sort of very informal way of thinking about this is that it's like the limit is just when you have like infinity f's here. And so then if you add one more f on top of that, it like doesn't actually do anything. That's kind of a goofy way of thinking about it. I mean, it sort of makes sense, I guess, but you can actually rigorously prove that whenever you have a situation like this, if this function f is continuous, okay, specifically it has to be continuous, otherwise it all breaks down. But if f is continuous, then if this sequence converges, the limit has to be a fixed point of f, where f of the limit equals the limit itself. Anyway, so we'll come back to that later, but I think it's a kind of an interesting thing. So now I dreamt up this insane looking sequence for you guys to analyze. And that's kind of, so it's going to look absurd, but that's kind of the point, is that like, we should be able to handle sort of complicated sequences just by, sort of thinking about them kind of qualitatively. You'll see what I mean. So this sequence is defined by, let's see, 1 plus 100 e to the minus n over 100 cosine of n pi over 100 and sine of n pi over 100, and then arctangent n pi over 1,000. So these numbers are all like kind of arbitrary, but whatever. So this is when n equals 1, 4, 7, 10, so on. This is when n equals 2, 5, 8, 11, so on, right? So there's words for this, which is like, this is when n is 1 mod 3, this is when n is 2 mod 3, and then this is when n is 0 mod 3. So 3, 6, 9, 12, so on, okay? So basically the sequence just kind of like cycles through these different formulas. And I want you guys to tell me what are the lim sup, and you don't have to prove it, of course. I just want you to figure out what they should be. Okay, so I'm actually going to go ahead and put you guys back into the groups. So yeah, let's take like 5 minutes for this one, because it's not a lot of work. It's just, you just have to think about it a little bit. So yeah, let's say we resume at like 5:47, and then I'll give you guys the last problem after that. So let's see. All right. Okay, so I did. Made a tiny typo. It doesn't actually affect anything, but I don't like having the pi in here just because that's not, our arctangent. The argument of arctangent is not actually measured in radians. So, I mean, you can put a pi there. It doesn't do anything. But yeah. Anyway, so I just deleted the pi. Actually, yeah, I'm gonna actually delete it. Okay. So let's see. So what did you guys get for the lim sup? Does anyone want to volunteer?
My group got pi over 2.
Yeah, that's right. So basically, right, this it's doing a lot of complicated stuff, but the real question is just like, what is the biggest value that these cluster around, or that the overall sequence clusters around, as you go like arbitrarily far out, right? So you kind of have to like think about just like what's happening to each of these things individually, and then kind of pick like whichever one achieves the biggest values, right? So let's kind of sketch. Let's sketch a little bit of like what's going on. So this first sequence, right? You can kind of just like sketch all three of them and sort of overlay them. So I'm gonna do this. Oops. And like that. So this is like, this top one is supposed to kind of be like, that's like the 1 plus 100 e to the, let's say minus x over 100 as like a curve, right? So the first thing here is kind of like oscillating between these two curves, and it's like approaching, this is like going to 1 and this is going to -1, right? Because this 100 e to the minus n over 100 ends up just going towards 0. So the amplitude of the wave up here approaches 1, right? And it kind of approaches 1 from like outside, right? So this wave is oscillating with big amplitude here, and then it gets smaller and smaller, but it's approaching amplitude 1. So sort of like the lim sup of this thing on its own would be 1, right? And then this one is the same way. So this one's actually just staying at amplitude 1 the entire time, right? So there's kind of this like, here, actually, let me see if I can do some kind of like fancy color thing. So here's the first one. And then the other one is like just in here. Oh God. Right. Although they have the same frequency, so I don't know, whatever, doesn't matter. And then the last thing, right, is just this like, arctangent literally just goes from like negative pi over 2 at negative infinity to pi over 2 at positive infinity. So pi over 2 is approximately like 1.5. So I'm going to, well, it's very out of scale. Also, this crossing happens like way further down here, but it doesn't matter. Right. So, and then this thing is approaching quote unquote pi over 2, if you could believe that that's where it would be. So anyway, yeah, so, the biggest values end up being around pi over 2, and then the smallest ones from the picture you can tell end up being at -1. Okay, so the lim inf would be -1. Are there any questions about this? Okay, yeah, so it's just this like really complicated looking thing, but in the end, all you have to know about it is kind of the general shape. And that's actually true, like, that's true for a lot of stuff in this class. Is like, in principle, when we talk about like arbitrary sequences, those sequences could be extremely complicated in their description or impossible to describe. But if you just kind of like get a sense of the general like trends and like general sort of scale that they have, then you can do a lot with that. Okay, so here's the last one, and this is kind of a tricky one. Hopefully this will be fun. I don't know. To me, I feel like there's something like fun about coming up with sequences that have these like weird combinations of properties. So give an example of a sequence that satisfies the limit of well, here, let me say this. So there are two properties. The first one is for all epsilon greater than 0, there exists an n such that Sn minus Sn plus 1 is less than epsilon for all n greater than capital N. And the next one is, or yeah, three properties actually. Sn is bounded. So this is kind of the key thing that makes this a little bit tricky, maybe. I'm not sure. And then Sn diverges. Okay, so yeah, we're a little bit tight on time. If you're, yeah, I'll put you guys in the groups, and we might have to resume at like 6 o'clock, and I'll go a couple minutes over. So if you have to leave before that, obviously that's fine. But yeah, I think this is a pretty interesting problem. So anyway, yeah, here we go. So yeah, let's resume at 6. Hey, so also I just realized during the break that I haven't been paying close attention to the this like participant screen. So if you were raising your hand earlier, trying to like ask a question or say anything, I'm really sorry if I missed it. I'm trying to. I mean, this is still kind of new for me. Also, it's just like I have to keep like 4 windows open on my screen at the same time, and one of them I can't even like. It's the whiteboard stays on top of everything else. Like there's no way to like select other stuff and have it be over it, which is really weird. So it's just, yeah, it's kind of crazy. But yeah, hopefully that doesn't happen again in the future. Anyway, was anyone able to come up with an example for this? This is a little bit tricky, and I know you didn't have a ton of time, so I totally. Oh yeah, sorry, Sagar.
Sagar.
Oh, Sagar. Sorry.
So we weren't able to actually put it into like we don't know like a closed form, but we're thinking something
Sure,
like
yeah.
this. Wait, I don't know if you can see the screen. Like
Um,
something where it's like a wave that like starts off like really like tightly oscillating and then slowly gets more and more spread out as it goes.
Yeah. Okay. Yeah. You have the right idea. I can't see your screen. Sorry, but yes. So that's exactly like the right idea, and this is definitely a situation where it's like you don't want to get hung up on trying to describe a formula for it. Like as we go on more and more, like the sequences that we'll be interested in will be sequences where it's like there's not just a numerical or like arithmetic formula for the values, but rather like you describe a pattern, like you describe a way of like determining the values, which might involve like a complicated algorithm or something like that, or maybe some kind of complicated logic or something that determines what the values are, or just like writing out a pattern or something. And so yeah, here's I can sort of give a precise version of the kind of thing you're talking about. So something like s1 equals 1, and then like maybe s2 equals 0, and then S3 equals like 1/2. Well, actually, let me just like list them off. I don't have to do all this. It'll be more compact. So like say 0, 1, 1/2, 1, 2/3, 1/3, 0, 1/4, 1/2, or like 2/4, right? 2/4, and then like 3/4, 1, and then so you get the idea. It just sort of like switches to steps of smaller and smaller size. So 4/5, right? 3/5, 2/5, 1/5, 0, and so on, right? That would be one way of accomplishing this. So yeah, I mean, proving that this does all of this stuff like really rigorously and formally could take a bit of time, but like you should be able to convince yourself that it's true that this satisfies these properties, right? Because the differences, right, the successive differences between terms are like 1, 1/2, 1/2, right? 1/3, 1/3, 1/3, 1/4, 1/4, 1/4, 1/4, and so on, right? They're well, the absolute values of the differences, I mean. And then it's just, obviously it's bounded between 0 and 1. That's just like sort of manifest. And it diverges because it consistently reaches the values 0 and 1 over and over again, right? Like it never stops going like all the way between 0 and 1. So it maintains this like fixed amplitude basically. Mm-hmm. So yeah, that's exactly what you're saying. It's a wave that basically like stretches out as you go out. So any questions? All right, great. Well, that'll do it then for the discussion today. And hopefully the new lecture will be up soonish. But I'll see you guys tomorrow, hopefully.
Thank you, Professor.
Thank you.
Bye.
Bye-bye.